Hello, everyone. So today we will discuss or we'll learn about infrared spectroscopy. In spectroscopy, we analyze the interactions between matter and radiation. Different kind of radiations uh, interact with matter differently, and those interactions are based on motions of electrons, protons, maybe atom bonds, and then how much energy is needed to create that motion. So I'll just give you an example. Uh, right, so when electrons are present within a system, they rotate, right? When they rotate, because electrons are charged particles, and when they spin around the axis, according as we know from laws of electromagnetism in physics, spinning of any charged particle creates a magnetic moment. Now, if we uh, place these kind of electrons in a magnetic field, that will create the two different energy levels, one where electrons can align with the external field, one against the external field. And then those electrons interact with electromagnetic radiation by going from lower energy level to higher energy level. And that is a field of spectroscopy called electron spin resonance. We're not going to discuss that today. I was just giving you an example. So in infrared spectroscopy, we analyze the interactions between matter, which is chemicals or molecules, everything is matter, with infrared rays. Okay, so I'll explain in more detail in a couple of slides later, but that's what infrared spectroscopy is. Okay. So before we uh, look at what infrared spectroscopy does to molecules, let's clear some of the concepts about radiation. All radiations, they are electromagnetic radiations. It means that they have two components. For example, if we look at visible light or ultraviolet light or any kind of other radiation, so they will have an electric component. So both of these components look like waves. So okay, so red one is if the wave is moving this way, and the red component shows the electric component. And all radiation, they have a magnetic component also, which is perpendicular to the electric component at 90-degree angle. So they both have, all radiations have electric and magnetic components. So that's why all radiations are known as electromagnetic radiations. And that is true for visible light, ultraviolet, X-ray, all radiations. Now, each of these radiations, each of these waves, they have wavelength. Now, wavelength is the distance between the peaks of the top of two peaks or the bottom of two crests. So these are called crests. So that distance remains the same. It is denoted by symbol lambda. Lambda has the units of distance, which could be meters, millimeters, centimeters, micrometers. Uh, the nature of radiation changes if the wavelength changes. Okay. For the entire electromagnetic spectrum, so this is just an example here. Let me see if I have the entire spectrum. I don't have the entire spectrum picture, but I'll just give you an example. Depending on the wavelength, the shortest wavelength belongs to a category of radiation called gamma rays. In this case, the wavelength is smallest. So in gamma rays, the radiation value is in the range of 10 to the negative 16, sorry, 10 to the negative 16 meters. That's the order in meters. 10 to the negative 16. It's extreme, up from 10 to the negative 16, maybe up to 10 to the negative uh, 14 or 12. So this zone is gamma rays. So it means the wavelength is extremely small. So the waves are tiny, 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 tiny. The distance is extremely small between the waves. Okay. So wavelength is getting larger. So larger wave this way. So it means, and on the extreme end of the spectrum, we get the largest wavelength. It means the waves there are like extremely large. So the distance between the two peaks is extremely large. And I'm talking about uh, 10 to the positive 8 meters large. It's extremely large. 10 to the positive 8 meter large is how much? It's about like 10 million, 10 million about, right? Or 100 million. 10 to the 6 is a million, right? So it's 100 million meters. So one wave crosses the entire planet of Earth, that large. So from here to here, so this side, we don't have to remember the number. Just remember the largest waves are radio waves, or largest wavelength waves are radio waves. Smallest ones are gamma rays. So we don't have to remember the wavelength numbers, just remember the order. After gamma rays, we have X-rays. After X-rays, anyone remembers what comes after X-rays? Is UV. After UV, we have visible. After visible, we have infrared. After infrared, we have microwaves. And then we have radio waves. The gap is not correctly in order. It's just uh, I mean, the values of this distance is not correct, the wavelength, but the order is correct. So the shortest wavelength is found in gamma rays, and the largest wavelength is found in radio waves. Okay. So that is the order of wavelength. Another thing we need to know is frequency. Okay, so frequency is number of waves passing through a point in 1 second. It is reported in units of hertz or second inverse. So hertz is a unit. It means how many of these waves are passing through one point in 1 second. Okay. All of these electromagnetic radiation, they travel with same speed, and that speed is speed of light. It is denoted by c. C is speed of light. The symbol is c. Anyone remembers what's the value of speed of light? It's a constant value.
3 times 10 to the 8th meters per second.
That is correct. That is correct. So value of speed of light is 3 times 10 to the 8 meters per second. Okay. So all of these electromagnetic radiation travel with same speed. Now, frequency is inversely proportional to wavelength. If wavelength is high, frequency will be low. If wavelength is low, frequency will be high. Okay. And if we multiply the wavelength value with frequency, it will be a constant. Okay. So wavelength times frequency. So lambda times, so symbol for frequency is nu, it's nu. It looks like a V, but it's a nu. It's Greek N. So frequency multiplied by nu is a constant value, and that constant is c, which is speed of light. So we can say lambda times nu is equals to c. So in other words, if you know the frequency, you can figure out the wavelength or vice versa, because c value is constant. So c is equals to 3.0 times 10 to the 8 meters per second. Okay. Any questions so far? Let's practice a problem. I'm gonna erase this order. Oh. I'm gonna draw this order one more time. So UV, it was X-rays here, and then gamma rays were the. Another important property of these radiations is the energy associated with these uh, radiations. Energy is proportional uh, to frequency. Okay, so energy of any radiation is given by E is equals to H times nu. H is a constant number. It's called Planck's constant. Okay. So energy is directly proportional to frequency, and the value of Planck's constant is 3.99 times 10 to the negative 13 kilojoules per second, no, kilojoules second per mole. Okay, I have to erase some of it. So it's radio waves here. Okay. In your problem, value of Planck's constant will be given to you. You don't have to memorize the value. Okay. It's a constant number. So energy is proportional to frequency. Higher frequency means higher energy, and frequency is inversely proportional to wavelength, which means that smaller wavelength means higher frequency, or in other words, smaller frequency, smaller wavelength means higher energy. So keeping these two concepts in mind, tell me which uh, radiation has higher energy, visible light or microwaves? Which one has more energy?
Visible light.
Everyone agrees with that, visible light? Visible light is correct. Right? Microwave has lesser energy than visible light. This may sound a little bit strange, because you may say, oh, we cook food in microwave ovens, but nothing happens in visible light. That's not because of the total amount of energy available. It is because how we use it, how microwaves interact with food particles. They interact with the water molecules, by the way. If your food doesn't have any water, it's not going to get cooked. So that's a different principle how it cooks. But visible light has more energy, because visible light has smaller wavelength than microwave. Smaller wavelength means their frequency is more. More frequency means energy is higher. Okay, so any question up to this point? So far, we have just reviewed what are electromagnetic radiations, and what is wavelength, what is frequency, and how they are related to each other. Any questions so far? Now, organic molecules are flexible. They have flexible structures. It means that the bonds can bend, they can stretch up to a point. The atoms which are connected, they can rotate. So they can show different kind of movements within a molecule. Okay, and all these movements, they are not random. Just like quantum mechanics of when we learn about quantum mechanics, we learn that that energy is quantized. Similarly, all these moments, they also need some energy, and those values are quantized. I'll give you one example which is relevant here. Oops. Okay, let me share another screen. Okay, for example, if we have, let's say, simple molecule C and H methane, right? And let's consider this bond, C and H bond, ignore the other bonds. So if C and H bond, if the black sphere is carbon and the red sphere is hydrogen, and they are connected with this bond. So this bond is this one. Okay, so actually what this, they are not fixed, they are not rigid. It means that these molecules are spinning this way. This can also be spinning, right? The other thing is that they are vibrating also. Vibrating means that they come closer to each other and they move away from each other, just like two spheres connected with a spring. So bonds, you can imagine the bonds are also springy. Means these molecules can go inwards or they can go outwards, just like spring. If they go inwards, the bonds become smaller. If they go outwards, the bond become larger. And this movement going in and out is continuous. It keeps happening. Okay. Now, when they come closer to each other, right, because they have electron clouds, these electron clouds start repelling. Okay, so they move farther away. Repulsions happens when they are too close to each other. When they are too far from each other, too far away, then there are nuclear interactions. Mean the nucleus of this molecule starts attracting the electron cloud of that one, so then there are attractive interactions. So when they are too close, they repel each other. When they are too far away, they attract each other. Okay, so if we plot this behavior, so distance between the nuclei, so this is the distance between two atoms in a bond, and then this is the force. So that's the attractive force, how much they attract each other, attractive force, right? So when they are too far away, the force is sorry, no, this is not, let me draw it first. It's actually the repulsive force. So when they become too closer, so the force is too much, and then that's the plot. So that's the distance, ideal distance. So at this distance, the force is minimum. So they like to have this distance. So this is the bond distance, by the way. If they go beyond this distance, even then the force is high. If they come closer to this distance, even then the repulsive force is high. So they don't want to do that. Okay. So they keep moving back and forth, back and forth, back and forth. So this is the vibration. Uh, okay. So any question about this concept, the vibration in the bonds? Because infrared spectroscopy causes these vibrations more intense. Okay. Okay. So in spectroscopy or molecular spectroscopy, uh, we study the frequency of electromagnetic radiation which are absorbed or emitted by a particular substance and the correlation of these frequency with details of molecular structure. Let me go back to my drawing there. What do I mean by that? Okay, so molecule wants to stay at this level, right? So any level, any other bond distance, it goes, if it goes harm, so this is the optimum distance. If the bond is stretched, then the distance is here, right? If the bond is stretched, distance is here, and then energy level is here. So that higher energy, right? So higher, so it's not, it's the energy. And we know that the molecule want to have as low, the lowest energy possible to be stable. So if the bond distance is increased, it means the bond is being stretched, then the energy of the molecule goes up, right? If the bond is squeezed from the ideal level, even then the energy is going up. Now, how much bond can stretch or squeeze? It's not random. It's a fixed number. It can be stretched either this much, so that energy, or it can be stretched this much, maybe that energy. So we call this is E0 value. E0 is the lowest energy. This is E1, first, second level, third level. Okay. So ideally, the molecule wants to have a bond distance of some ideal distance. So that's where the repulsive and attractive forces are optimum and they are at the lowest possible energy level, most stable. If the bonds are stretched, the distance goes up. Distance goes up means the energy goes up. And if the bond is squeezed like a spring or is compressed, even then the distance goes down. Even in that case also energy goes up. So it creates a different levels. Okay, so going from one stability level to another level, so it means in order to go from some optimum bond distance to higher or lower bond distance, you need more energy. And this energy is matches up with the energy from infrared rays or infrared radiations. So it means if you have a bond and the bond is at, imagine this is optimum distance, okay, and infrared radiation falls on it, this radiation gives enough energy to this bond so that it can squeeze, right? Or it can expand, because in squeezing the bond distance or decreasing the distance, energy is higher. So that energy has to come from somewhere in order to do that, and that matches up with infrared. Or if the bond expands, you know, is stretched, even then it needs energy, and that energy comes from infrared. And that is the basic principle of infrared radiation. Infrared radiation causes vibrations in bonds. So bond starts vibrating more. Now these vibrating levels are quantized. It means that they need to absorb a specific amount of energy to go from optimum level to some certain compressed level, or from optimum level to some expanded level. And how much energy, we'll take a look at it in next slide, what that value is. But it's not a random number, they're a fixed number, and that number depends on what kind of bond we are talking about. CH bond has some other energy level. Similarly, CO bond will have some other level, and so on. Depending on what kind of bond is there, the level of energy is different, and all of those levels fall within the range provided by infrared radiations. Any question? I'm sure you guys have some question. Hello? Any questions, anyone? Everything is clear, nothing clear? Some confirmation would be great.
I think it makes sense so far.
Okay. So how about rest of the class?
Yeah, it's clear so far.
So
Yeah,
far it's
that's
okay?
yeah.
Please let me know if it doesn't make any sense, or if I need to go over some topics again. I'll be more than happy to explain one more time, because I don't think this is given in the book. Okay. Okay, so that's what infrared radiation is. Just to summarize, what we can say is that infrared radiations, their energy is enough to cause vibrations in the bond. Okay, vibrations in the bond means that the atoms which are connected at the ends of the bond can come closer or can move away from each other. So the bond can be either compressed or can be expanded, just like a spring. So bond is not a rigid stick or rigid, thing. It's a flexible, so it can be compressed or expanded. And if the bond is compressed, molecule come closer, which causes repulsion, and energy of the system will go up. That's a unstable system. If the bond is expanded, even then the energy of the system goes up. That's also unstable. And in order to go from stable to unstable level, system needs energy, and that energy comes from the infrared radiation. So it means when infrared radiation fall on a molecule, the bonds can absorb that energy, and that absorption of energy gives them enough. That absorption of infrared radiation gives them enough energy to go from stable level, where the bonds are at optimum distance, to go from either compressed level of the bond or expanded bond. Both of the cases will require more energy, and that energy comes from infrared. So infrared spectroscopy is also known as vibrational spectroscopy, because it causes vibrations in the bond. Okay. So infrared spectroscopy, infrared frequency is in this range, and we can calculate the energy from this frequency, and we can exactly calculate what the energy is. But anyway, so it's also known as vibrational spectroscopy because it causes vibrations in the bond, or vibrational energy levels. Okay. For NMR, the levels the energy level falls in radio frequency, and for UV visible spectroscopy, of course, it falls in ultraviolet or visible range. But in this chapter, we only gonna focus on infrared. In infrared spectroscopy, uh, let me go back here. Let's say I have a molecule, it has right. So in this molecule, as you can see, we have different kind of bonds. Can you name few bonds which are present in this molecule? Can you name any bonds present in this molecule? What kind of bonds are present? All are covalent bonds, okay? But I'm talking about between what kind of atoms are these bonds. Okay, I'll get started. We have CH bond, some CH bonds. Can you name any other bonds in this molecule?
You mean
C
like
double
the
bond.
polar bonds?
Polar, non-polar, all kind of any bond. So
C
one
double
kind of
bond.
bond is CH bond. Any other bond present in this molecule?
There's a C double bonded to the O.
Okay,
then-
that is another kind. Any other kind?
O.
The C double bonded to the Cl.
You mean C single bonded to Cl? What do you mean C double bond? Cl, that's a single bond, not a double bond.
Yes, I meant single bond, sorry.
Yeah, okay. Any other kind of bond?
The O
CC.
bonded.
CC bond, yes. Carbon-carbon bond. How about C and single bond O?
Then the OH bond.
O and H bond, right? Okay, so that's all. So even within a single system, within a single molecule, we have, in this one, we have 6 different kind of bonds, right? And when infrared ray fall on them, all of these bonds have different kind of vibrations. So this has different vibrations, this has different vibrations. So they all have different vibrational levels. If they have different vibrational levels, it means that they will need different energy, right? Yes?
Yeah.
Yep.
Fortunately, infrared radiations, their wavelength or their frequency, well, let me confirm. I don't want to give you a wrong number. I think I have it there in this one. Falls from, wavelength falls from this value 2.5 times 10 to the negative 6 to 2.5 times 10 to the negative 5. Okay, let's go back. So all these energy levels falls, okay, so 2.5 times 10 to the 6 meters to 2.5 times 10 to the negative 5. I want to give you exact, I had it somewhere written here. Just give me a second. Let me find exactly the number. We can calculate from here. Okay, so that's the wavelength, right? So this is the, so all radiation has a range of wavelength. So in this case, the range is from this number to that number. So let's calculate the frequency. So frequency, we can calculate the frequency from here and calculate the wave numbers. So infrared radiation has enough energy to cause vibrations in all of these bonds, although their energy requirement is different, but because there is a range of frequencies within the infrared radiation, that is enough to cause vibration in all of those. Now, it means that if we plot wavelength, it's not the exact plot, but I'm just trying to explain the principle behind it. Some of these bonds will absorb or will have less energy requirement, and some will need more energy requirement. And I'll give you an idea that if the bond is more polar, then it would vibrate at more energy. If the bond is less polar, it will vibrate at less energy. Just it's a oversimplistic because there were different kind of motions present, which we'll learn in a couple of slides later. But that's a simple idea. So it means CC bond, CH bond, they will vibrate at low energy or high energy. If the
Lower.
Low
polarity
energy.
difference is less, they vibrate at lower energy. If the polarity difference is more, then they vibrate at higher energy. It's an oversimplistic version, but that's enough for now. So what can we say? CH and CC bond, will they vibrate at lower energy or higher energy?
Lower.
Lower energy.
Lower energy, right? And similarly, OH will vibrate at high energy, right?
Yeah.
And CO will also be relatively high-ish, right? High-ish, because that's also, but OH will be the highest, right? CO and then Cl. And another thing, it depends on the strength of the bond. So double bond is stronger than the single bond, right? So that will also be kind of higher. So if I have to look at it, so low lambda and high lambda, or low frequency and high frequency. And this way is absorption. Absorption of radiation, the plot. So maybe at this level, none of the bond will absorb because these values are quite specific. So although, so we won't see any absorption, right? And then at certain level, OH will absorb. OH is the high energy, right? So high energy means wavelength will be low or high?
Low.
Low. So OH will absorb somewhere here maybe, and we'll get a peak, right? And then nothing happens at some other frequency, maybe CO will absorb maybe here, and some other frequency, maybe something else will absorb, and something, so lowest energy, maybe CH will absorb, and so on, or CC will absorb. So we will get some kind of a graph. Now, if we look at the graph, the high energy is on the left-hand side and low energy. So high energy is at the low number. So low lambda is high energy and high lambda is low energy, which kind of gets confusing. So instead of plotting the graph versus wavelength, what we plot is we plot graph versus wave number. Okay. Now, what is wave number? Wave number is inverse of lambda in the units of centimeter inverse. Okay. how do we calculate wave number? I'll give you an example. For example, if we have a wave and wavelength is, let's say the wavelength is 1 meter, let's say, and calculate wave number. So first, because we need units of centimeter inverse, that is key thing. So first we need to convert this into centimeters, right? So 1 meter has how many centimeters? 100, right?
Yeah.
So first convert this into centimeters. So 100 centimeter. And so wave number is, so wave number is denoted by symbol, there's a nu but with a bar on top. So that's a symbol for wave numbers. Okay. And so this will be equal to 1 divided by wavelength. So 1 divided by 100 centimeter, or it's equals to 10 to the negative 2 centimeter inverse. So this is the value of wave number in this case. Okay. Let's try another example. So here in our case, we said the infrared vibrational value goes from 2.5 times 10 to the negative 6 meters to 2.5 times 10 to the negative 5 meters. Right. So let's calculate wave number for this one. So let's calculate the range in wave numbers instead of so first, let's calculate for this one, 2.5 times 10 to the negative 6. So wave number for this one will be equals to 1 divided by 2.5 times 10 to the negative 6. Now it's meters. We need to convert that into centimeters, right? So we'll use the conversion factor 1 meter 100 centimeter, right? That's the conversion factor between meters and centimeters. So meters and meters cancel. So we have centimeter, units of centimeter inverse. So this will be equals to 2.5 times 10 to the negative 6 times 100 centimeter down here. So if we solve this whole thing, we will get so these two together is 2.5 times 10 to the negative 4 centimeter, and this is equals to 10 to the positive 4 times 2.5 centimeter, and when we divide it, we will get 4,000 centimeter inverse. Okay, so that's the highest wave number on this end. Let's calculate the other value. How about you guys give it a try? 2.5 times 10 to the negative 5, and let me know what value do you get. So we converted the smaller wave number. Now let's convert 2.5 and tell me the wave number of that range.
400 inverse centimeters.
Okay, so when we convert that, so wave number in that case will be 400 centimeter inverse. Okay, so it means infrared spectroscopy will have wave number or will have vibration range from 400 centimeter inverse to 4000 centimeter inverse. And that's the range within which all the bonds will show vibrations. Okay. You can calculate energy also if you want to by applying the E equals H nu. You have to calculate nu first, but that's unnecessary. We don't need to. But if you are interested, you can calculate. And that's where the range 4,400 comes in, because uh, we convert the wavelength value, vibrational wavelength, into wave numbers. Okay, so this is an example of a infrared spectrum given by this molecule, something similar, and you can again see it, this molecule has different kind of waves. We don't worry about it, we'll learn about how to interpret this data, but for now just I want to show you the value. The top scale, that scale is the micrometer scale, so that's a wavelength, and the bottom scale is the wave number. In actual spectrum, we do not pay attention to top scale. So we don't even look at the top scale, micrometers. That is not even, it's not even given in many cases. And on this side is the transmittance. Remember the plot which I absorbed, sorry, the one I plotted here, that was the plot, this one. That was absorbance, how much energy it absorbs. The actual practice, we plot transmittance, how much energy is transmitted. Let me explain. So because this molecule has some kind of different kind of bonds, and they absorb energy at different levels. So at 4,000 wave number level, or this wave number energy, everything is transmitted, means nothing is absorbed. Yes, about 10% is absorbed, but that's background, something else is absorbing it. Molecular bonds are not absorbing it. So that's we don't, so we consider this as a baseline. So we consider this as a baseline, although the baseline has to be at 100%. Baseline means that's the level where no absorption is taking place. So everything is getting transmitted. If no absorbance is taking place, then 100% should be transmitted, right? But we can see it's not 100%, about 90% is transmitted. So that 10% loss is a background loss. So we cannot overcome that. But anyway, so at 4,000 level, no bond is absorbing the energy. So all the energy is being transmitted. And at this level, which is about, what is that, 33-ish something, 3,300 wave number, right? Something absorbed, right? But that's a really low absorption. So if the baseline is 90, so how much percent light is absorbed here? 6 or 7% wave, right? Not a high amount of absorption. So tiny peaks, many times we ignore. We just focus on the main peaks. So the first main peak is at this level. And in infrared, we always talk about the range. So this is from 2,800 to 3,000. Okay, right? So that's a strong absorption. So it's going all the way up to 20. What does it mean? It means at this wave number level, some bonds absorbed a lot of energy. So only 20% light was allowed to transmit, 80% was absorbed. So that's why the plot is upside down, is flipped, because we are now plotting the transmittance, not the absorption, right? Although these are not peaks, surprisingly, we still call them peaks. They look more like valleys now, but we still call them peaks in infrared. Normally we would refer these as peaks, but even these upside down, we still call them peaks. So again, nothing absorbed from 2800 all the way up to maybe 1700. And then we have a sharp peak at 1700. So only this much light is being transmitted. It means 90% is absorbed, only 10% is allowed to transmit. So whosoever is absorbing, that's a strong absorption signal. So very little transmitted, and so on. And then rest of the peak, or absorption peaks are there. So that's what infrared plot looks like. Okay, so we look at the range where the main peaks are being uh, are showing absorption. Infrared data or spectra is split into two sections, one higher than 1400, this side, and then this side. This, the lower than from 1400 to 400, this side is called fingerprint range. Okay. In fingerprint range, we get tons of peaks, tons of data, but it's almost impossible to interpret it. So we use it as fingerprint. We can be used to match two unknowns together. If the fingerprint, just like we match fingerprints, right? So we just match those peaks together and then we can say, oh, these two are same, but we cannot interpret it. And the peaks which we normally interpret what's present in the in our system, that is anywhere that's from 1400 all the way up to 4000. So any peak in this range, that is analyzed. So this is the analysis zone. So fingerprint range, we don't analyze all the peaks. We don't interpret any peaks. Okay. So this we already have learned that covalent bond undergo continual vibrations. That's the one I was discussing earlier, that covalent bonds are kind of like a spring and they vibrate and they can go. So the energy is quantized, means going from one level. So that's the optimum distance. So that's the lowest energy. We call that E0. That's the stable level. And then so this is distance. And that's the energy going from this level to next level. So these are quantized. It means it can only go from E0 to E1. That's the allowed transition, or E1 to E2, or E2 to E3. It cannot go from any random number between E0 or E1. That's the meaning of quantized. And in order to go from higher to higher energy level, it needs energy, and that gap falls within the range of infrared rays. So it means when infrared radiation falls on the bonds, they give them enough energy so that the vibrations go from one optimum distance to either expanded distance or compressed distance. So all those vibrations fall in this infrared region, which is 4000 wave number to 400 wave number. Although we call them wave numbers, but they are still energy associated with this wave number. If you want, you can calculate wave energy, because you know the relationship between wave number and wavelength. And from wavelength, you can apply this formula E equals h nu. So first you need to convert wave number to wavelength. Then from wavelength, you need to calculate the wave frequency, and then you can calculate energy. But that's if you want to calculate energy. in the plot, we plot them versus wave number. That's why we don't need to calculate the energy. Just remember, wave number has the direct relationship with energy. So high wave number means high energy. They are directly proportional to energy. Wavelength was inversely proportional. So that's one reason why we don't plot versus wavelength. Why do we plot versus wave number? Let's go back. Oh. Now in a molecule, we may have a different, like 7 or 8 or maybe more than 10 different kind of bonds, but not all bonds will be able to absorb infrared radiation. For a molecule to absorb infrared radiation, it needs to have it needs to meet certain criteria. First criteria is that the bond must be polar. Okay, and the polar bond doesn't mean the polarity we discussed so far. Even the tiny change in electronegativity sometimes is enough to make the bond polar. For example, C and H bond. Do we consider CH bond polar or non-polar?
Non-polar.
We consider earlier non-polar. That's for solubility part of mainly, right? For calculating solubility. But if we look at the dipole moment, or if we look at the electronegativity, carbon is 2.5 and hydrogen is 2.1, right? For infrared, this is enough. That's enough polarity. Okay, so spectroscopy, even the tiny amount of difference in dipole, electronegativity, that's enough to create this polar environment within the bond. So CH bond for infrared is polar. So this will absorb. But if it's CC bond, now this is purely non-polar. So then CC bond, will it absorb?
No.
It will not absorb. So only the pure non-polar bonds do not show infrared signal. Any tiny amount of variation, that will be enough. I'll give you another example. If we have a molecule, something like this one, it's a symmetrical triple bond, like C triple bond C. And that's non-polar, right? So what do you think? Will it be able to absorb the infrared radiation? The answer is no, it will not, because it's non-polar. However, instead of if we have this compound, so here, so this one is not infrared active. Well, not the entire molecule, I'm talking about the CC bond. You understood it. Now, if we look at this bond, this is non-symmetrical. So in the right-hand side, we have one carbon and one hydrogen, right? On the left-hand side, we have bunch of carbon and bunch of hydrogens. Yeah. So that difference, because there's a difference in number of atoms, that difference is enough to create polarity. So this is active, IR active. Okay. So so we can generalize that for a bond to be IR active, it must be polar, first of all. Okay. And secondly, if a bond is present in asymmetrical environment for a double or triple bond, if it's symmetrical, then they are not active. But if it's asymmetrical, then it will become IR active. Okay. For a nonlinear molecules containing n atoms, there are 3n minus 6 allowed vibrations, kind of vibrations. For example, if I have, let's say, simple molecule. Okay. How many atoms are there in this molecule?
5.
5. So total number of vibrations which this molecules can show, different kind of vibrations, is equals to 3 times 5 minus 6 equals how many?
9.
9 vibrations. 9 vibrations means how many peaks I will see in my NMR, sorry, not NMR, IR plot? 9 different kind of peaks. And that's for this simple molecule. Imagine if I have something more interesting, something like that. Now in this case, you can imagine it's going to multiply really, really fast. So it's 1, 2, there are hydrogens. I don't want to calculate, but it's going to be dozens, if not hundreds of peaks, right? So if your molecule becomes significantly larger, we will have dozens of peak. I have a number for ethanol. So ethanol is CH3, CH2, and OH, right? So in ethanol is C2H5OH. So how many total numbers do we have? 7, 8, and 9, right? So total is 9 atoms. So how many vibrations are possible in ethanol?
21.
21. And ethanol is not even a big molecule. It's only 2 carbon long chain. And we know that in organic compounds, we can have some really large. If another one I calculated was hexanoic acid, it's 6 carbon long chain. And if you calculate in hexanoic acid, the total number of peaks comes out to be 54. So the point here is interpretation of all those peaks and all those valleys and vibrations is impossible. So we cannot interpret this structure correctly from infrared spectroscopy. But we do get extremely important information, and that information in combination with other spectroscopy data such as from NMR and from mass spec is enough to analyze and elucidate the structure of the molecule. So IR alone is not enough to give you entire picture or the entire structure of the molecule, but it does provide extremely important information. It does provide what functional groups are present. It will not tell you it's 6 carbon long chain or something like that, but it will provide you information regarding whether there are double bonds present or not, whether there's a functional group, what kind of functional group is present. All that information will be obtained from infrared spectroscopy. Okay. Let's take a look at a pattern of motions or stretching. We call the stretching and bending vibrations in methylene group. We are only focusing on this part. We're not focusing on the other two. So this CH2, that's a methylene. In methylene, there are 6 kind of vibrations are possible. Individually is just one kind, but in combination with other bonds, there are 6 kind. So first one is called symmetric stretching, means this bond is also going this way, the other bond is also getting stretched this way. Okay. Second is asymmetric stretching. So one is getting pulled, the other one is getting squished. Okay, so that's asymmetric. In symmetric, both are either getting pulled or both are either getting. So these two are stretching vibrations. Then it shows bending vibrations. In bending vibrations, bonds do not stretch, they just bend. So the bond angle changes. That also happens in infrared spectroscopy. So the first is called scissoring. Scissoring means both bonds are going inwards or outwards together. Okay, that's scissoring, just like a motion of a scissor. Rocking means rocking like a rocking chair, so going this way and then maybe backward. So this and backward, both of them doing together. So that's rocking motion. So this is called rocking. Okay. Next one is wagging. So wagging is just the direction is different, but it looks kind of similar to rocking, but just the direction is different. So both are going this way and backward. Last one is twisting. So bonds are getting twist this way and then backward. So these are the vibrational motions of stretching and bending of methylene group. And this is the simplest molecule. If you go more complex, we don't even know, we can't even see the all dozens or hundreds kind of patterns. Fortunately, we don't need to know all those. What we need to know is how to analyze the this IR spectrum. Okay, let me see here. Yes. Okay. Now consider a bond, any bond, and is connected with connected to 2 atoms, and we said in infrared it vibrates, so we consider bond to be like a spring. Now spring vibrates, right? It goes back and forth. The motion of this spring can be calculated by applying laws of physics. This is similar to simple harmonic oscillator. So if you apply the concept of simple harmonic oscillator, so we can calculate. Now that physics part is beyond my expertise, so I'm only gonna give you the final expression. That value comes out to be 2 pi c n. This is kappa, not k. It looks like k divided by mu. Okay. C is speed of light, is a constant. This is known as Hooke's law. So So he calculated applying the concept of simple harmonic oscillator, and he found that the wave number of any bond which is oscillating is proportional to, is equals to this whole expression. Let me first give you what they are. So c is speed of light, that's a constant value. N is Avogadro number, that's also a constant value. Okay. So K or kappa, this is a force constant. That's also a constant. And force constant is proportional to whether the bond, it's proportional to the strength of the bond. Okay. And Hooke calculated, and for a single bond, this value is equals to 5 times 10 to the 5. The units are dynes per centimeter. So dynes are, for double bond, it is equals to, double bond is approximately 2 times as strong as single. So the force constant is 2 times as force. And for single triple bond, any guesses what will be the value of K?
15 times 10 to the fifth.
Yep. Okay. So these again, K, this is also constant. So 2 is constant, this is constant, this is constant, and N is also constant. K is a sort of a constant, but it varies if your bond is double, single, or triple. Now mu, the last one is mu. What is mu? So mu is, sorry. So mu is called reduced mass. So if the bond is connected to 2 atoms, let's call this atom number 1, it could be any atom, let's call this atom number 2. So reduce is, mass is calculated by mass of atom number 1 multiply, it's not molar mass, it's mass of one atom, okay, times mass of atom number 2 divided by this. Okay, so this is called reduced mass. Okay. Imagine that, let's apply this. Let me tell you how to calculate the reduced mass. Let's say we are calculating for C and H. Okay. Okay, so C, if we have 1 mole of carbon, how much will it weigh? What is the mass in grams of 1 mole of carbon atoms?
12.
12 grams, right? And how many atoms are in 1 mole?
6.022 times 10 to the 23rd.
So it means 6.02 10 to the 23 atoms equals 12 grams. So mass of one atom, or mass of 6.02 times 10 to the 23 atom is 12 grams, right? So mass of one carbon atom equals 12 gram divided by 6.02 times 10 to the 23, right? So that's how we can calculate mass of one atom. We take the molar mass, we divide with the Avogadro number. And similarly, we can calculate for this one, and we can calculate the reduced mass. Okay. When we plug in these values, 2 is a constant, pi is a constant, c is a constant, n is also a constant. When we plug those values in, so the Hooke's law changes to this value. So 4.12, this is Hooke's law, which we can. This is the expression for Hooke's law, which you should memorize or remember. And okay. Any question about Hooke's law? If we look at Hooke's law, we'll see that the wave number expression, it depends on k directly. Higher k value means wave number will be higher or lower.
Larger.
It will be larger, right? And how about the mass, reduced mass or mass? Higher mass value or reduced mass value means mu or wave number will be, or signal where IR signal gonna show up will be higher or lower value.
Lower.
It will be lower value, right? So it inversely is it. So the wave number of any bond is inversely proportional to the mass or reduced mass, and it's directly proportional to the kappa or the strength of the bond. So for example, if I have C and O bond and C and double O bond. Now in both cases, because C and O are same, therefore their mu value will be same in both, right? But because the bonds are double and single, that will be different. Tell me which of these bonds will be at higher, will appear at higher wave number. Which one? C single bond O or C double bond O?
C double bond.
And that is correct. So if I have a plot and I know that it is showing peaks, so this plot is from 4,000 to 400. And if my plot has only 2 peaks, so one at, let's say at 1800 and the other peak at maybe 800, and I know that this has C and O, then which peak belongs to C double bond O and which peak belongs to C single bond O? So this is the range 400 to 4,000. So we just said that the higher wave number belongs to this one. So 1800 peak will belong to this one, and lower wave number, which is belongs to this one, right? Does that make sense?
Yeah.
Okay. Similarly, let's say I have another IR. And this again, the range is 4,000 to 400. This is the range, by the way, and they are all in centimeter inverse of wave number. And I have signals from C H bond and C and O. Come on. CCl bond, let's say. And I have 2 signals, and I know that one of the signal belongs to CH bond and other signal belongs to Cl. Okay. And maybe I have one signal here and the other signal here. Okay, let's call this signal number 1 and signal number 2. Based on the information from Hooke's law, Can you tell me which one belongs to CH? Is number 1 signal belongs to CH or number 2 signal belongs to CH or vice versa?
Two belongs to CH.
Okay. Everyone agrees with that? Okay, so let's see. Both of these have single bonds, right? So kappa value is same. So kappa is out of the picture, right? How about the mass or reduced mass? Reduced mass is directly proportional to the total mass, by the way. So which one is heavier? The combined mass. Which one is heavier? CH heavier or CCl is heavier? Combined.
CCL.
CCl is heavier. And we know that heavier mass, so here, kappa. High kappa, sorry, not kappa, mu. So high mass means high mu. So high mu means wave number will be smaller or larger?
Smaller.
It will be smaller. So it means CCl will be number 2. And CH will be number 1. I'm sure you guys have questions. Please let me know. Is that okay? Does it make sense?
Yeah.
So there are only 2 things to look at. One is whether it's a double bond, single bond, or triple bond. The other thing is combined mass. Higher combined mass means that the signal will appear at smaller wave number value. Okay. Now 2 is here. So remember, this side is 400 and this side is 4000. So if I have to, so maybe this is 2000, right? So this number will be, if I have to guess, what 2800 maybe? Is a good estimate? Yeah.
Yeah,
Yeah.
seems about right.
This would be maybe 1400. I don't know, just I'm guessing, right? So that's the smaller wave number. And we just said that higher mass means smaller wave number. So that's how I interpreted that number 2 belongs to CCl and number 1 belongs to CH. Okay. Let's try one more based on the Hooke's law. Or we can go to the next topic, whatever you like. Another problem or go to the next interpretation of data?
Professor, I just have a
Yes.
question and
Yes, I was waiting
just
for
a little
that.
clarification. So the wavelength of these, to what extent is it influenced by the other atoms attached to the carbon in question?
Do a little bit, but not a lot. You mean if something else is attached here?
Yeah, like assuming that the Cl is attached to that CH and possibly a CO as well, or there's an oxygen, chlorine, and a hydrogen.
Yeah. So the thing is that let's say I have this molecule. Imagine, right? Now this bond is vibrating back and forth, and this bond is vibrating back and forth. And these 2 bonds sort of are almost independent of each other. The vibrational motion, they have their own vibrational motion. They do interfere a little bit, but that value doesn't change. So if we apply, I have a calculation with me. I'm not gonna do it again. But according to Hooke's law does not consider anything else connected to the bond. So Hooke's law interpretation is based on 2 independent atoms connected to a bond. So according to Hooke's law, nothing is on this side, nothing is on that side, right? That's the limitation. So if we apply Hooke's law to CH bond, right? And we apply this force constant and mu, we calculate exact number. And you know what wave number theoretical wave number value comes out to be? That value comes out to be 3,332 centimeter inverse. So according to Hooke's law, that any compound, if it has a CH bond, it should show peak at what value?
3032.
3032. But when we actually do the experiment, we don't get at 3032. Okay, so according to Hooke's law, you should get just one single peak for all CH bonds at 3032. And in actual practice, we don't. What we get is we get the value anywhere from 2800 to 3000, anywhere for CH. So why there's a discrepancy? That's the answer to your question. Yes, the other motions interfere. But Hooke's law is close. It gives you approximate value. See, it's close enough. But it will alter a bit. But it's not gonna change a lot. And I'll show you next slide how much discrepancy is from Hooke's law to actual value. So that's why in infrared, we don't report one single value, we report a range. Because the bending and stretching will be affected by neighboring environment. So that's why it's not always exactly same value for CH or same for CO. It's not going to be same value. It'll be close. It'll be within a range. Okay. Does that answer your question?
Yeah, it makes sense. Is it, I assume it gets more complicated when it comes to polarity and if it's a ring structure and all that.
Yes. Yes. So for a ring structure, it changes different. For example, aromatic CC bonds, they vibrate at totally different values, and aliphatic, they vibrate at different value. We have a table of values which gives us some number, and we can use that table and we will apply that information to calculate different, presence of different bonds.
Okay, makes sense. Thank you.
Any other question? So Hooke's law is theoretical interpretation of these vibrations. So it will give you theoretical value. And that theoretical value is close enough to experimental value, by the way. It's not absurd. It's not totally different. But experimental values will differ slightly from a theoretical value calculated by Hooke's law, because Hooke's law considers each bond to be independent of other bonds. But in actual practice, all these bonds are connected to each other, so they will have some effect on the vibrations of neighboring bonds. Okay. Okay, so this is Hooke's law. Okay, and these are the values of force constant, and that's the reduced mass. Okay. So Hooke's law will tell you the position of the peak. Okay, so if this is our IR spectrum, so 4,000 wave number centimeter inverse all the way up to 400, all the peaks will be within this range, and this way is the transmittance. Now the position of the peak, so that's 2,000, that's 1,000, 3,000. According to Hooke's law, CH bond was where? At 3,000, right? And if you calculate Hooke's law, you will find the CO bond comes somewhere around 1,500. So this is again calculated from Hooke's law, approximately 1500. So the position of Hooke's law, the position of bond is depends on the kappa value and the reduced mass. Because CO is single bond, CH is single bond, so kappa is same or K is same, and the mu reduced mass is smaller in CH, that's why it's at higher wave number, and larger mu means the position will be lower. The other thing is intensity, how intense the peak is. Some peaks are intense, like all the way down here, and some will be faint. Okay, so for example, at around 2200, we get a faint peak, and this peak is if there is a triple bond present. So triple bond comes at around, according to Hooke's law, about 2200. Now, why the intensity is less or the peak is smaller, or the size of the peak? Intensity means size of the peak. That depends on the polarity. More polar the bond is, okay, more intense the bond will be. We know that the carbon-carbon triple bond, if asymmetric, it's asymmetric. Symmetrical doesn't even show up. So if it's asymmetric, it does show up, but the polarity difference is extremely small. So that's why the intensity is extremely little. So intensity depends on the polarity. Okay, and the position depends on whether it's a double bond, single bond, triple bond, or the mass, reduced mass. Okay. So this table gives you approximate values of some of the bonds and their positions. So we can see these are the approximate ranges. And again, the intensity means how strong the peak is. More polar bonds are strong and less polar are weak. And OH is a unique situation. If the strength of OH bond depends on whether it's hydrogen bonded or not. Okay, so it can be anywhere from extremely strong peak to a weak peak, depending on if it's hydrogen bonded or not. Okay. Okay, so is it possible for you guys to note down these values? Because we're gonna use these values in next slides. And I will like you guys to participate. You can click a picture or maybe note down some of these values, because we'll need this. Everything okay? You guys got it?
Yeah.
And maybe this
Yep.
also. This also. Click a picture or note it down. Now we're gonna start the main part of this chapter, which is the interpretation of infrared data. Okay, everyone got these values also?
Yeah.
Okay. So the way I'm gonna discuss is we go from alkanes, alkenes, alkynes, and then different functional group, and we will see what to be expected and how to analyze the data. Okay, so we start with alkane. So ignore the top scale. So ignore it. We don't even need to look at it. Okay. So in alkanes, infrared spectrum is one of the cleanest spectrum. It means it will have the minimum amount of peaks. There'll be very few prominent peaks. Okay. The most prominent peak you will get will be at around 2800 to 3000. Okay, so we discussed just a few minutes ago. Can you tell me what this peak is? Which bond this peak represent? According to Hooke's law, we just discussed. at around 28 or 3000.
The CH.
This is CH, yes. Okay, so CH bond, oops, sorry. Oh, sorry about that. Okay, so how do I change the view? Okay, I have in the slideshow, it doesn't let me remove these boxes. So, okay. Okay, so at 2800, the peak is CH stretching. And look at this characteristic pattern. You see there's a one sharp peak that is characteristic CH in alkanes. Okay, so okay, another characteristic peak you will obtain is this one, which is 1400 to 1500 in the middle of that. If you look at your table, what can you tell what this peak is?
It's CH2.
See, in IR, we always say whether it's a stretching or bending. So for
Or-
example, at 2800, this one or this one is CH stretching. So what would it be? Would it be stretching again or bending, or what kind of peak?
Bending.
So say that again, which peak you think?
CH3 bend or CH2 bending.
Okay, so we have two peaks. One is this one, the other one, that one, right? Okay, so how about this one? The smaller one.
That one CH3 bending?
And you guys are correct. So this is CH3 bending and this is CH2 bending. Why CH2 intensity is more than the CH3? Because we have more CH2s compared to CH3. Okay, so only three prominent signals will be observed in alkanes. One will be at around 1450 to 1475. That would be CH2 bending. And then CH3 bending will be a little bit less or lower value. So that's why we know, because CH3 bending is anywhere from 1375 to 1450. So you can see it's below 1400. So it has to be CH3. That's one way of knowing it. Okay, any question about alkane IR spectrum? And like I said, we don't really care about, we don't interpret most of the peaks in fingerprint region, although there is a peak here, but we don't need to analyze that. Okay. Okay, so the next one is alkenes. So this spectrum belongs to cyclohexene. In cyclohexene, you will see fingerprint zone is quite busy. So anywhere from here to here, from 1400 to 400, the right hand side, this is fingerprint. So we not going to analyze. The main peaks are labeled here. So the first one is again little more than 28. So it's 2800 to 3000. So what do you think? What is this peak?
It's the CH.
Bending or stretching?
Stretching.
It is CH stretching, yes. Now, so see, so I wrote here aliphatic stretching because This CH, it shouldn't be aliphatic, it should be sp3. So this is the CH bond which is connected to carbon sp3 hybridized or alkane. So it means it doesn't, okay. Let's first go over it because it doesn't let me write on the slide here. And then you will see this peak right after the CH stretching. There will be a single sharp peak, and this peak belongs to CH, which is connected to the double bonded carbon, or sp2, CH connected to sp2 hybridized carbon. So that will appear at this position. Okay, so this will be a strong signal. Usually comes a little bit more than 3000. So this one always higher than the CH sp3ch hybridized. Okay, so this presence of this sharp peak after the CH stretching, that indicates the presence of a double bond. That is characteristic of alkenes. Okay. Now, how about this one? This the one here. Excuse me.
That's the CH2 bending.
This was again CH2 bending, just like alkanes, because it still has CH2 groups here. And then we will get this peak at around 1700, a little bit less than 1700. If you look at your table, what do you think? What is this?
It's the double bond.
Is a C double bond C. And you can see the intensity is extremely low. And in many cases, we don't even see it. In many cases, it doesn't appear. In cyclohexene, it's there, but sometimes it's extremely small or it's within the baseline, so we don't see it many times. So presence of a double bond can be indicated by this peak. This is a C stretching. C stretching a higher mass. That's why it is at lower wave number value, but it does not appear all the time. However, this CH stretching, which is CH connected to the double bond, that will always be there. So even if this peak CC stretching not available or is not visible, we can still predict the presence of a double bond by looking at this peak. Does it make sense?
Yeah.
Yeah.
Next one is alkynes. And in alkynes, again, this peak you probably already know. What is this peak? Between 2800 to 3000. What is this one? I have
CH.
not even labeled it now, but you should know it now. What is this?
Just the CH stretching.
Yeah, so CH stretching these ones, the ones sp3 hybridized, right? Can you please let me know if you see my cursor moving?
Yeah, we can see
Yeah.
it.
Yeah, you can see it.
Because I'm unable to write in this way, and I cannot remove the boxes in PowerPoint presentation. So, okay, so from these are sp3 hybridized CH or carbons, right? So these CH stretching comes from 2800 to 3000. So now you know these are characteristic patterns. In alkenes, the CH, which is connected directly to the double bond, was right here, right? At a little bit more than 3000, right? In alkyne, this CH, the CH directly connected to the triple bond, that shows up at 3250, somewhere in that range. So this one is a characteristic stretching pattern of hydrogen connected directly to C triple bond C. Okay. How about this one? I have not labeled it, but what do you think? That's around 1450, this peak.
The CH2 bending.
The H2 bending is correct. See, now you are picking up the patterns. There is one additional peak here, moderately intense, not super intense, but still there. So what is this peak? Look at your table.
The triple bond.
Yeah, so that's around 2200, right? Or 20 in that neighborhood, right? And this is C triple bond C stretching. And again, triple bond stretching will only appear if your alkyne is asymmetrical. For terminal alkynes, it's really easy to see. But if your triple bond is somewhere in the middle of the molecule, then this bond disappears. Can we still know whether there is a triple bond present or not if we have an alkyne which is symmetrical? Can we still somehow figure out that this is alkyne?
Yeah, we use the CH bonded to the CC triple bond.
Yes, you are correct. Do we look at this one? This will always be extremely intense because that polarity difference is enough. So any question about how to analyze IR spectra of alkanes, alkenes, or alkynes? The similarities and the differences. Can anyone name the similarities between these three spectrum? Any two peaks which are similar? Give me the position where the similar peaks will appear, at what range?
The CH peaks between the 2800 and 3000 seem to be constant.
That is correct. So that is CH stretching. So that will be same. That will always be in there. And then what other?
CH2 bending.
CH2 bending and the range?
From like around like 1400.
1400 to 1475. Yes. Yeah. Yes. By the end of this lecture, you will remember most of the ranges. Okay. Let's go to now aromatic. Now, aromatic hydrocarbons are a little bit different. Again, there are three characteristic peaks. So this is a spectrum from toluene. Now, toluene has CH aliphatic, which is CH3, right? And those are here 2800, these ones. Okay. Aromatic CH, so these are the hydrogens connected directly to the ring. So those show up above 3000. So this is a characteristic pattern of aromatic CH. Okay. So between 2800 to 3000, that belongs to CH3 part. So this CH, aliphatic, these ones. And aromatics are these ones. If it's only the benzene, then this part will be absent. Anyway. Another characteristic pattern in aromatic compound is in the fingerprint. Normally, we do not analyze the fingerprint zone, but for aromatic, this is CH bending of aromatic, these two peaks. Okay, so around 700. And then this is a C double bond C stretching pattern of aromatic hydrocarbons. Okay. So this position is similar to alkenes, but this one is a new one. So when we have two of these together, that indicates that this system is aromatic. Okay. Next one is alcohols. If in alcohols, there are three, of course, the CH stretching and CH bending will still be there. But the new peaks to observe is for CO and OH. The CO peak will appear between 1000 to 1250, and OH peak, that's the most important. This peak will be on the leftmost side or the highest, because OH is one of the most polar bond, and intensity will be, because it's a broad peak, that's why it doesn't appear that high, but it's still absorbing a lot. And OH peak is characteristic by nature because it's so broad, and it's at generally at around peaking at around 3300, but it could be anywhere from 3200 to 3600. Or 3500 if it's hydrogen bonded. If it's free, then it will be relatively sharp peak. It will not be broad if it's not hydrogen bonded, and it will be at around 3600. Most of the IR signals you will get will be a hydrogen bonded OH. Most of the time it is hydrogen bonded. Extremely few OH molecule. There are extremely few molecules with OH group which are not hydrogen bonded. So free OH signal will be a rare case. Okay, so this one is 1000 to 1250, so that is CO stretching, and this one is OH. How about this one? Anyone? So this is at around 2800 to 3000. So what are these peaks?
CH stretching.
CH stretching. And how about this one at 1450-ish?
CH2 bending.
CH2 bending, yep. And how about this one?
The CH3 bending.
CH3 bending, the terminal CH3, yep. Ethers. Ether spectrum will be similar to alcohol, only difference is there will be no broad peak here because there is no OH group. It still has a C double bond O, so that will appear at around 1000 to 1200, somewhere in that range. It will still have the CH2 stretching and CH3 bending and stretching, so all those will be there, but it will not have that broad. So it's extremely easy to distinguish between ethers and alcohols. Okay. Amines. Okay, let me just remove that. So these two peaks we already know. This one is CH2, CH3, and these are, we already know that. Now for amines, we get not so broad, and we get a doublet. This is a doublet. If our amine is a primary amine, we get doublet. And we get a singlet. This will be a single peak at this position if we have a secondary amine. Singlet for secondary. Okay. So whenever we see a doublet here at around 3300 or 32 to 33, we can say it's a primary amine. And if we have a weaker these signals are weaker than alcohol and less broader. So if it's a singlet, we'll say it's a secondary amine. Any guesses why doublet in primary and singlet in secondary? If you're thinking that because in primary there are two NH and that's why we get double, and in secondary there is only one NH bond, that's why we are getting singlet. That is not correct. So doublet in a is because it could be a symmetrical stretching, and the other one would be asymmetric stretching. Okay, so one of the peak is because of symmetric stretching, the other peak is asymmetric stretching. In secondary amine, there is only one NH, so there is no meaning of symmetric or asymmetric, so that's why we get only one peak. How about tertiary amine? What would it look like in case of tertiary amine? Yeah, it's okay. Any guesses is it? It's correct or acceptable. What do you think? What tertiary amine spectrum would look like?
Would it just not show?
And why?
Because we have minimal polarity.
Your answer is half correct. Yes, you are correct. In tertiary amine, there will be no peak. So no peak at 3200 to 3400. Why there will be no peak? Because the peak is NH. Do we have NH in tertiary? Do we have NH bond in tertiary amine?
No.
We don't. So that's why in tertiary amines, there is no peak in this range. Okay. And these two are the same ones, CH2 bending, CH3 bending. Okay. And the last category of IR patterns is from carbonyl containing group. In all the carbonyl containing group, the common theme is that they have CO. It could be ketones, could be aldehyde, could be carboxylic acid, could be amides also. They all have C double bond O. Okay. C double bond O peak, this one is a high intensity peak, and it's anywhere from 1600 to 1820 for ketones, 1600 to 1820 for aldehydes, 1700 to 1725 for carboxylic acid, and same zone and same for amides also. Okay. In case of ketones, that will be the only prominent peak. However, in carboxylic acid, we will also get a broad peak from OH group. It will be even broader than alcohol. I'll show you an example in a while. And in case of aldehyde, we'll have another narrow peak, that's the CH stretching connected directly to CO at 2720. That is also unique and characteristic peak. Let's take a look at some examples. Amides, this data is here. So that's amide, that's ester, acid anhydride, and nitriles. Nitriles are cyanides. You can see the data here. Okay, let's look at example of a ketone. So this is a ketone, cyclic ketone. So that's a ketone peak. It's gonna be extremely, now C double bond O and C double bond C, they both stretching. Both are around 1700. Both of them are. How can we distinguish them? If we go back to alkenes, where is alkene? Yeah, that's also around 1700, right? Ketones also around 1700. How can we distinguish them?
Based on intensity.
Based on the intensity, you were correct. Alkene double bond, C double bond CA is extremely weak. And this will be high intensity. Yes. So based on the intensity. And the rest of the peaks you already know. So this is CH stretching. And how about this one? What is this?
CH2 bending.
CH2 bending. That is correct. And maybe this one.
CH3 bending.
Yep. And these we don't need to worry about. This is just a fingerprint zone. Okay. Any question about ketones? Carboxylic acids. Let me see what this is. Oh, we'll come back to it. In carboxylic acids, the OH, see in alcohol, the OH was like that. And then at 2800, we have this one, right? So this one was OH in alcohol. And these ones at 23,800, what were these in alcohols? CH, right?
Yep.
Look at what happened in carboxylic acid. It is so broad that it encapsulated the CH bonds. It's even broader than, it's so broad that it's now all the way going from here to 2800. That's the OH stretching. It's extensively hydrogen bonded. That's why it makes it extremely broad. How about this one? What is this peaking from the broad peak?
The stretching CHs.
Yeah, stretching CHs, right? So the OH has overlapped. OH peak is now overlapping with the CH peak, but we can still see them. And this is the CO carbonyl from this part here, and this is also broad. Okay. In carboxylic acid, all peaks generally get broader. How about this one? What is this peak? It's from 1400 to 1450-ish. Anyone?
Is that the CH2 bending?
Yep. CH2 bending. CH3 bending, I don't see it. So maybe they are so broad, they merge together. That happens sometimes. I don't really see it. But this is an indicative of a carboxylic acid functional group. Infrared spectroscopy is more meant to figure out what kind of functional groups are present. And it does wonderful job in doing so. Esters. Now, esters have a characteristic C, O, O, and R. Now, there is CO group. Can there be hydrogen bonding in esters? Is there a chance that esters may show hydrogen bonding?
No.
Answer is no. That's why you can see the peaks are so sharper and narrower. And there is no OH. So no OH group. No OH group means no peak here. No broad peak in that zone. Okay, so that's one way of knowing it. This one is obviously the carbonyl, and these ones are stretching of CH bonds. That's the CO bond. This CO bond will be absent in ketones. So this bond not present in ketones, because ketones do not have a C single bond O. Esters, they do have this bond at around 1200. Anyway, it could be anywhere between 1000 to 1200. In this ethyl butanoate, it's at 1200. So that's one way of distinguishing esters from ketones, presence or absence. Let's go back to our ketone. See, at 1200, CO peak is absent. Okay. If we have a cyclic carbonyl compound, the position of carbonyl peak varies with the stability of the cyclic compound. We know that 6-member cyclic compounds are more stable, and 3-member are less stable, more strains, or less stable. Less stable means high wave number. More stable means low wave number. So more stable the group is, the signal of CO will shift to lower value. Okay. Same concept is applied here. So more resonance. So this can show resonance here. So this can go here, this can go here, and more resonance, right? So this can also go here. So in this one will be more resonance. And in this case, no resonance. And here, one structure, right? Some resonance. So resonance also pulls, well, there is more to it. So if there is any resonance, then also the absorption will be at lower frequency or lower wave number. But it's not that significant. It's a slight change. Okay, so that's all about infrared spectroscopy. Now we have some problems to analyze, but any question about how to interpret the infrared data, or how it works, what it is, the theory behind it? Any questions so far?
So,
Yes.
so with certain instances that you've shown, an abundance of a particular bond seems to at times intensify the peaks. Would we see the same behavior in a far more complicated compound, like testosterone or something that has a bunch of different attachments to it? Would that show just crazy amounts of peak, or we'd see some sort of familiarity?
The crazy amount of peaks will be there in the fingerprint region, because even in testosterone, how many functional groups you think it has? Not that many, right? Yes, it may have lots of CH bonds, and yeah, the intensity will be higher, but the crazy amount of number of peaks will be in this in the fingerprint zone. But if it has a functional group, so those peaks will still be, yes, it's not going to be as clean as this one. Yes, for sure. It will be, but it will still be, it still will not be that difficult. I think we can, in Beyond's lab, we have IR, but I don't think we have testosterone there, but we can pull up a complex molecule and see what the spectrum looks like, IR spectrum.
But there will still be discernible information outside of the fingerprint.
Yes, there will be still, yes, for sure.
Okay, thanks.
Okay, so let's see what kind of problems we may encounter in this IR chapter. So I'm gonna show you two spectras later on. Next slide. One spectra belongs to hexanol, this one, and the other one belongs to nonane. And you need to tell me which one belongs to hexanol and which one belongs to nonane, okay? Everyone understands the question? I'm gonna show you a spectra now. Remember, one of the spectra belongs to hexanol, the other one belongs to nonane. So this is alkane. We already know what alkane spectrum gonna look like, and this is alcohol. What do you think? Is it hexanol
Hexanol.
or
Hexanol. Yeah.
everyone sure about that? How do you know that this is hexanol? What made you say that it's hexanol?
It has like the OH peak at like 30, like 300 or something, 3 to 400.
Yep, that is the OH stretching. Okay, so while we are at it, so let's label all other peaks. So hexanol is CH3. Right? So we already said this is OH stretching. How about this one? What is this peak?
CH stretching.
I normally write sp3. That means that this carbon is sp3 hybridized. That indicates that it is from alkanes, or no double bond. So CH stretching. You're gonna get problem where I may give you a IR spectrum and you have to label the peaks, and that's how you label it. So nothing from 1600 to that. So how about this one?
CH2 bending.
Any other peaks you would like to label?
Is that one CH3 bending?
At what position approximately?
Approximately looks like 1380, maybe.
This one?
Yeah.
And you are correct. Yep, this is CH3 bending. Any other peak? Or is this it?
Wouldn't that be like the CO bond at like 1,500 ish?
This
Or
one?
1,050, sorry. Yeah. Like CO.
This is CO stretching. Yep, these are all the peaks for alcohol. Yep. So if you see an alcohol spectrum and you are asked to label, you should try to label these peaks. So in alcohols, you will have OH stretching, CH stretching, CH2 bending, CH3 bending, and then CO stretching. Yeah, CO stretching is between 1000 to 1200. In this case, it's 1050, but in some other alcohol, it may move slightly. So now this should be easy. So what is this?
Nonane.
This is nonane. Nonane. Let's label it. Excuse me. So in alkanes, how many peaks do we label normally? Only 3. So let's start from the left-hand side at 2800. What is that?
CH stretching.
How about this one, the middle peak?
CH2 bending.
And the last one is CH. We don't need to worry about rest of the peaks. Any question about this problem? Let's look at another problem here. Okay. In this case, we need to identify the signals you would expect in the diagnostic region. So diagnostic region is from 1400 to 4000. the other than the fingerprint. So let's talk about A. Let's look at A molecule and name all the peaks you expect to see in A.
CH stretching.
So we expect to see the CH stretching at what position?
2800 to 3000.
Okay. Anything else? Any more prominent peaks? Let's talk about the main prominent peaks. You can look at your data table if you want to.
The C double bonded to O.
The carbonyl, right? At what position?
At 1600 to 1800 or so.
Yep. Right. How about B? So this is for A. How about B? What peaks do we expect to see?
The
Ignore
CO bonds.
ignore the 2800 one. That's gonna be there all the time, no matter what organic compound you do, because all organic compounds gonna have a CH, right? So let's ignore the CH at 2800 because that's always gonna be there. Let's label other than that.
The
What other
CO
peak?
bond.
CO, and at what position?
1000 to 1200.
Yep. And anything else? Now in this case, it's asymmetrical, right? Alkene. And on the right hand side, there's a O. So that oxygen gonna withdraw the, because it's electronegative, so it's gonna make this side different in polarity than the left hand side. So there's gonna be enough polarity difference. So now I expect in B molecule, the CC double bond to show up, and it should show up nicely. And that's gonna show up at around, again, 1650-ish. And of course, there will be CH stretching at 2800 and those usual ones. So let's ignore that, right? Let me see what I have for answer. Ooh. So the same thing. So for the double bond, 1600 to 1800, and then, yeah. How about C? Do we, will we get the double bond, C double bond O, sorry, C double bond C signal, this one, the alkene?
No.
No.
So do you think this alkene is a symmetrical alkene? Remember, asymmetric alkenes do show up. Is it symmetrical?
No, it's not. So it should show up.
It should show up, and it will show up nicely. So remember, symmetric means you look here, right? So the top side is different from the bottom side, right? So it's not symmetrical. So it will show up. How about the triple bonds? Will they show up?
Yeah.
Again, this is terminal, and then of course this one is also asymmetrical because it's right on the side. So triple bonds will also show up, and C double bond O, that will also show up. So here C double bond C and C each should produce a nice signal, and they will probably be in the same region, but you will still be able to see. And then C triple bond C will also be a nice signal there. Last one, D. It's an carboxylic acid. So what do you expect to see?
The OH
And what kind of OH?
stretching.
Yeah, so, and anything unique about this OH signal?
It's like big or like wide.
It will be so broad that it will overlap with
The CH stretching.
Yes, yes. Any other prominent signal? There'll be CO signal at 1650-ish, right? And all the signals will be broad. So it's gonna be extremely broad signal. This one is interesting. So in this problem, we have 6 different IR spectra, and then we have 6 molecules we have to match. Let's go one by one. Let's go A. So what do you think? A belongs to what? Let's go with the easier one. Which one you are sure that spectra belongs to which molecule? Any of this which you are sure this is that one? Anything you can match?
So
E.
C.
Oh,
C?
Oh, C would
ahead.
go to like the first one. The just like the simple hexane
So C belongs to this one.
or pentane. Yeah.
And why do you think so?
Has the 3 prominent
You are right.
peaks.
You are right. Yeah, you are correct. I'm just when I look at your thought process. How did you come up to that conclusion?
It's like it just has like the CH stretching on like the CH2 like
Yeah. And then so
bending.
it has
and
3
then-
peaks, right? This one, and this one.
Yeah.
So it's alkane. So that's why it's okay. You're right. Okay, so 1 is done. 5 more to go.
Shouldn't A belong to the alkene?
A belonged to alkene. And what was the key factor which led you to decide? Yes.
It has that initial dip before hitting the CH stretching.
This one?
Yeah.
And that is right. So this one is the C double bond C, this stretching. So that peak is here. So that's unique for alkenes. Do we see any C double bond C stretching? Right? At around 1600, yeah. And all these are CH stretching. So this is alkene. Okay, 2 done. 4 more to go.
E would be the carboxylic acid.
Yeah, that is, and obviously, right? So look at how broad this is.
Right.
Extremely broad.
D should be the alcohol, right?
So that broad signal along with that C double bond O, that would be CO signal. That's the OH signal, right? This one. So that means this belongs here. That is correct. What else you said?
D would belong to the alcohol.
And that's again correct because this is broad OH signal, but not as broad as D. So this is alcohol. And only alcohol we have in our reserve is this one. And then other peaks. What is this peak?
It's the CO stretching.
Yep. And what is this peak?
CH stretching.
Yeah. And then this one,
CH2 bending.
CH2 bending. You guys are expert now. Okay, so 2 more to go. It's easy now.
F
What do you
should
think?
belong,
What's the meaning of this? Is that a unique thing here happening in F?
represents the nitrogen attached to the 2 hydrogen.
Yeah, that is a representative of primary amine. So this is NH in primary amine. So only amine we have is this one. So that is the amine. Yes, you can analyze rest of the peaks also. We have one left, and that has to be ester. What is this peak?
CO stretching.
CO stretching. And what is this peak?
The C. Oh yeah.
Right. And then last, let's finish it off. What is this one? CH stretching. Okay, so the main topic or main problem from this chapter you're gonna see is interpretation of data, or where the peaks will be. Like 90% of the problems will be based on that. Few problems will be based on Hooke's law. It will ask, oh, identify which one will have lower wave number. According to Hooke's law, 2 bonds will be given, and you will need to ask which bond will have lower wave number, which one will have higher wave number, so on. And very few problems will be based on calculation of wavelength or lambda, frequency or energy, E equals to h nu, or those kind of formulas. How confident you feel that you can answer those problems? Let's start with the interpretation of data. Analysis of peaks. Can we figure out what functional group is present, or how to label the peaks if the spectra is given to you?
Yeah.
Yeah, it's pretty straightforward.
Okay. How about comparison of bond wave numbers based on Hooke's law? That means
Might take a
yes.
little more practice on that one.
Okay. And the comparison of wavelength and energy based on E equals h nu, or lambda times nu equals c, those formulas, those kind of problems, can we solve those?
Yeah.
Yeah.
Or calculation of wave number if the wavelength is given, or calculation of frequency if wave number is given, and so on. Conversion of those. Will that be okay?
Yeah.
Now,
Yep.
the main focus, like I said, is the interpretation of data. So we're not done yet. I have more problems, so we're going to continue more. Okay. So now we had a compound, and compound is C6H10 and O. That's the molecular formula of compound. So ignore this one. And we get this. Can you tell me what? So all of these compounds are this one, but only one is the correct answer. Think about it, and please include me in your thought process. So think loudly, whatever you're thinking, just say it, and then we'll come up with the answer. Okay, so let's go. So what compound out of these 8 molecules labeled down there will give this spectrum?
We can eliminate the alcohols.
Okay, and why are you eliminating the alcohols?
Because there's no
I know why you are.
OH.
I'm just gonna make sure that everyone knows it. So just say it. Why alcohols are eliminated?
There's no OH stretch at the start of the spectrum.
So no broad peak here. So no peak here, right? No broad peak here. So that's why we can eliminate the alcohol. And So this is gone. This is gone. What else is gone? That's it. Okay,
think-
what else we, okay, so that's a good start. Yes, let's continue forward.
It has to contain a carbonyl because there's a high intensity COO peak there.
Yeah, wonderful.
1720.
Yeah, so high intensity peak means that there has to be a CO. So what can we eliminate now? Can we eliminate this one?
Yep.
Yeah.
And
The
let's
fourth
call them
one.
1, 2, 3, 4 and continue. So what number? So if this is 1, that's 2, that's 3, 4, 5, 6, 7, and 8. Can we eliminate any other?
4 and
4 and
7.
7.
4 is gone and 7 is gone. Oh, okay. Getting better. So now,
It has to have like a C double bond C because like the 1650 peak.
that is a good find again. So 1650 peak is C double bond C stretching, right? So what can we eliminate now?
2.
2 is gone. Okay, so now what? What is it? Is it 5 or is it 8? Right, so there are two more options, two options left, 5 or 8. Or is it impossible to figure out? Please include me in your thought process.
Would it be 8? 8
And
because there's a CH stretching, but there's no CH. Oh wait, never mind. Sorry. Not 8.
there are CH stretching in both.
Yeah.
It'd be 5 because there's only one CH3 and the CH3 peak's not that intense.
Yeah. So you base your decision on what peak?
Oh, would it be 5
The
because of
CH3.
the CH2 peaks?
Okay. 5 is correct, and you maybe are correct in that case also, that there are more CH3s in no. I don't know why. Again, let me listen to your logic again. Why 5 and why not 8?
Well, 8 has
2 CH3s.
2 CH3 and 5 has 1. I know we have nothing to compare it to, but I'm just saying that the CH3
No, that's not. The intensity comparison is not wise,
yeah.
because intensity is quite misleading. It may be quite high, maybe low. We never compare intensity.
Okay.
Okay. So the actual thing which you should compare is the value of CO. CO is at 1720. And what is the effect of resonance on CO? If you remember, if there is a resonance, sorry, this resonance, what happens to this CO value? It becomes at around 1600. Let's go back. Sorry. There. 1690. No resonance at around 1720, right? With resonance, 1690. Yeah.
Yeah.
So let's go back here. So what is our value? Is it less than 1700 in 16 something or around 1720? It is 1720. So that means, can there be resonance?
No.
No resonance. Out of 5 and 8, is there any one which gives resonance?
8.
8 gives resonance. So that means 8 is out. So the correct answer is 5. Okay. So any question about this problem? Does it make sense? Yeah, the last part was a little bit challenging, but if you go through the slides and remember all the concepts, you should do well. Let's try another one. I think I have another one here. Okay. In this case, you need to identify how IR spectroscopy might be used to monitor the progress of following. And we have done that in Beyond's lab, by the way. Remember, before the reaction and after the reaction, we did something and you attached a spectra there. So tell me how we can distinguish the progress of this reaction based on the IR. So I'm just gonna approximately draw the before and after. Okay, so what characteristic property you would look for?
The relevance of the CC double bond.
And what will happen to CC double bond peak? And where would that be?
We should see it diminish as the product becomes more prominent.
Wonderful. Yep, that is correct. And where it just, I know you know it, but just so that everyone else knows it, tell me more precisely at what position you would look for that peak.
Between 16 and 1700.
And that is correct. So if this is the spectrum, so of course we're gonna have a bunch of peaks here at around 3000, right? And what are these peaks?
CH stretching.
CH stretching, and then this is 2000, that's 1000, and then we will have a okay. So this peak at around 1600 to 1800. This is C double bond C. It will be present in the beginning. That's what you're saying.
Yeah, it will
And
be
it will
present.
disappear. It will disappear. Yeah.
Correct.
So why would it disappear?
Because we end up with a symmetrical molecule.
And that is the correct answer. So we are going from asymmetric alkene to symmetrical. Therefore, C double bond C signal will disappear. And that's the, yep. Okay, so I can give you more problems if you like, but before we do that, how do you feel about IR spectroscopy now?
Makes sense.
Makes sense? Would you like to try a few more problem, or we can stop here? Up to you. I'm gonna post a assignment That would go towards your lab assignment for this activity. So in this, but it will open after the Thanksgiving break, and it will be due, 7 days after. So next following Sunday. So it's not gonna. I'll probably open it before if you get time, but it will not be due on coming Sunday. It will be due Sunday after Thanksgiving weekend. If Is that okay?
Yeah.
And that report mainly will focus on analysis of IR data or analysis of spectrum. So mostly questions something like this one or this one. Okay.
And will this PowerPoint be on Canvas?
Yes, I will provide the PowerPoint on Canvas. Yes.
Okay.
Any other question?